Imagine standing in the vast, silent landscapes of the Arctic or Antarctic, where the ground beneath your feet is mostly solid ice, locked in a frozen state for thousands of years. But what happens when the brief summer warmth touches this ancient cold? This interaction creates a dynamic zone that is far more active than its perpetually frozen counterpart. What exactly is this layer, and how much of it awakens each year? The active layer is the uppermost layer of ground in permafrost regions that thaws in the summer and refreezes in the autumn. Its depth can vary significantly, ranging from just a few inches in some very cold, isolated areas to over 10 feet in warmer, wetter locations. This seasonal thawing and freezing is a fundamental process shaping polar ecosystems and has profound implications for our planet. The primary reason for this wide range in active layer depth comes down to a delicate balance of heat transfer. Factors like air temperature, the amount of solar radiation hitting the ground, and the length of the summer season play crucial roles. But it is not just about the weather. The type of soil, whether it is sandy or clay-rich, and its moisture content greatly affect how quickly heat can penetrate. For example, moist soils conduct heat more efficiently, potentially leading to deeper thaw. Vegetation cover also acts as an insulator, shading the ground and preventing deeper thaw, while a dense blanket of snow can protect the ground from extreme cold but also delay thawing in the spring, or conversely, insulate it from very cold air during winter. Understanding the active layer means observing these changes. Scientists use specialized probes called thaw tubes to measure how deep the ground thaws each season. These measurements help track the permafrost table, which is the boundary between the active layer and the permanently frozen ground below. By consistently monitoring these depths, we can observe long-term trends and better predict how these frozen landscapes will respond to changing environmental conditions. Beyond just depth, the moisture dynamics within the active layer are also critical. As water from melting ice moves through the soil, it creates a phenomenon called cryosuction, drawing nutrients and small particles with it. This dynamic process influences everything from plant growth to the stability of the ground. Knowing the exact thaw depth is also vital for engineering projects in polar regions, as structures must be designed to withstand the annual freeze and thaw cycles without collapsing or sinking. Ultimately, the variable depth of the active layer serves as a sensitive indicator of environmental change. Its dynamic nature directly impacts infrastructure, influences plant life, and plays a critical role in the global carbon cycle by affecting the releases of ancient organic material. By paying close attention to how deep this active layer becomes, we gain crucial insights into the health and future of our polar regions and their connection to the wider world.